Okay, so let me formally introduce you. We have Colin Elliott from Burker, who is going to talk about the Fourier 80 and its applications.
Thank you. So I'm Colin Elliott. I'm the product manager for Benchtop magnetic resonance product lines at Bruker Biospin. And I have to start with a terrible confession. I am pretty much a novice at NMR. I'm sorry. So actually, I'm an engineer by training and started my career up in Silicon Valley in an actual garage startup. It was a garage. And we were developing a different type of benchtop spectrometer, which was EPR or ESR. And this product became the micro ESR, which maybe some of you have come across. To cut a long story short, the micro ESR and myself joined Bruker about 6 or 7 years ago. And I stayed mostly in the EPR domain until last year when I was given the opportunity to lead the entire benchtop program. So the products include the ESR 5000, the mini spec, which is our time domain NMR, and of course, the Fourier 80, which is the subject of today's talk. So I am not yet an expert in NMR, but luckily I'm not here alone. I'll be joined by Dr. Alec Beaton. Alec is an NMR application scientist from our headquarters in Billerica, Massachusetts. Alec is relatively new at Bruker, but has already proven himself to be an outstanding addition to our team and something of a specialist in the Fourier 80. So please, when we get to the Q&A, give me your easy questions and save your hard questions for Alex. Or if you have really hard questions, we have some very lovely salespeople here who can pretty much handle anything. So let me know. So yes, today I'll be starting with a very high-level overview of the Fourier 80, introducing it to the family, discussing some of our key software and accessories, and then give a few examples of Fourier 80 in the lab. And then later in the talk, Alec will dive into the gory details of NMR with some specific examples. So to talk about the Fourier 80, I'd like to start back in time just a bit to talk about Bruker. We're a bit new to the benchtop game, but certainly have some experience with NMR. Over 60 years today, actually. And in this time, Bruker has stayed focused on 3 things: high quality products, versatile, strong focus on customer needs. If you've ever had the pleasure to shop for a Bruker spectrometer, you'll realize we don't exactly mass produce and stock the shelves like Best Buy. So each of our systems, we try to configure and optimize for our specific customers to help them solve their real-world problems. So to use the metaphor from earlier, we're more like the micrometer on the right, the big do-it-all thing, which we try to make sure is customized for your needs. And we bring that philosophy with us to the Fourier 80. For that reason, we've developed 4 members of the Fourier 80 family, which I will discuss in a little bit of detail and talk about some specific applications of each. So starting with the one we fondly refer to as the workhorse, this is as close to a standard system as we offer. This is a proton-carbon system. It works hard, it does your NMR, and it has a huge range of applications, including basic research in chemistry, biology, and material sciences, measuring bioprocesses in industrial fermentation, and teaching NMR in the classroom. Each system ships with a complementary education kit that you can use to teach your labs. Next system is the high performer. This is the grade A student. This is the overachiever. It does one thing and it does it very well, which is measures protons. So if you want to do lots of sample measurements or have very low sample volumes, this is quite useful. With such applications as conducting clinical studies in research and universities, high throughput quality control in different sort of industries, and monitoring reactions on the fly in real time. Third, we have the multi-talent, the guy that can do a little bit of everything. In addition to protons and carbons, you can measure fluorine with this, which of course is quite useful in certain industries, such as developing drug formulations, measuring fluorinated substances in cosmetic and oral hygiene products, and identifying unknown substances in forensic labs. And last but not least, we have the specialist. This is the oddball of the family, the nerd. He likes to go measure other type of nuclei in addition to protons. We have many different configurations available, some of which include the proton lithium probe for measuring and testing batteries, proton sodium probe for food and beverage analysis, and proton boron for quantifying byproducts in brines. I think we have about 8 of these options now, with more coming, and please check our website or catalog for the full list. So that would cover the basic configurations, but of course we have more versatile features, and this one maybe is particularly of interest to you because this is what we our system, and that's the software. And we are proud to offer 2 distinct software packages with the Fourier 80, which can be selected depending on your skill level. So for intermediate and advanced users, which I expect is most of the people in this room, we have something called Topspin. And this, yes, is the full deal, the full package. This is exactly the same software as comes with our high field systems, all the features, assisted acquisition, a fully configurable method development environment, non-uniform sampling methods, flexible task automation, and a huge array of analysis tools available. So with Topspin, you're getting decades of software development for NMR along with your Benchtop system. For those of us who may not be quite so advanced, we have another software package, which is called GoScan. So GoScan provides a simple, intuitive interface for the Topspin environment. The user is guided through data acquisition simply by selecting or customizing an experiment and pressing go, similar to using one of your smartphone apps. After acquisition, the spectrum is available for viewing within GoScan, or can be easily exported to other software such as Topspin or MNOVA for further analysis. Additionally, it has advanced user management options to keep those pesky grad students from messing up your system, although they'll probably break it anyway. So we also have a wide array of accessories, which I will go through very quickly. Some of the key accessories. We have the PAL RSI sample robot. So this is for automated sample handling and remote operation. Pulse field gradients for artifact suppression and for quicker analysis, or quicker acquisition rather. Adjustable temperature control for in situ sample tempering. Reaction Lab is our complete reaction monitoring solution. We have Chem Lab for chemical mixture profiling and reporting, and Crime Lab for narcotics profiling and reporting, as well as dissolution DNP readiness for hyperpolarization experiments on your Fourier 80. So all that and more, and of course we're developing new solutions all the time, including one coming very soon. I won't give it away, but if you're interested in the talk by Magritech earlier in the day, you might also be interested in this. And it will be described in more detail tomorrow at the Burker Symposium by our president, Falco Buse. So please join if you'd like to see that and all the other latest news from Bruker Biospin. And I promise that's my last plug for the symposium. I just wanted to mention one more feature that I think might be interesting to many people here, which is if you already happen to have a high field NMR lab, the Fourier 80 is an excellent complement to that. It goes in 2 directions. Starting with high field NMR, you can do thorough sample analysis of your samples and then use your benchtop systems to run routine analysis, thus freeing up your system, your high-end systems for other use. And with topspin, you can even transfer your methods and your pulse sequences directly, making this very easy to do. In the other direction, starting with low field, you have GoScan, which is a great entry point into NMR for students or for new researchers who haven't yet made the dive. They can start with GoScan to get used to it, familiarize themselves with topspin in the benchtop environment, and then they are ready to dive in to high field NMR and join your ranks. So now I'd like to point out two specific groups who are doing these sort of things. I'd like to start with the Dr. Andre Simpson Research Group at the University of Toronto, who you might also know as these lovely people in the back who just arrived. Hello. Dr. Simpson, of course, is well known for his work in NMR in addressing environmental problems at the molecular level. Some of his lab members shown here are all participating at ENC, so please keep an eye out for their posters and presentations. And you won't have to wait long because Dr. Ronaldson will be presenting right after this one. Here's a peek into their lab. Thanks for the photo, Katrina. You can see in addition to the advanced NMR spectrometers, Dr. Simpson has complemented that with the Fourier 80, including a PAL RSI sample robot. And since these are very advanced users, of course, they are using topspin. So we look forward to seeing what you will be presenting at ENC this year. And finally, I'd like to point out Dr. Evan Zhou's group at the Radboud University in Nijmegen, the Netherlands. So Dr. Zhou is using NMR for studying electrochemical energy storage and conversion. And here we can see their experimental setup, which is particularly dear to my heart because they've included EPR in the mix. What they've done is use their high field systems to characterize the degradation products formed during redox flow battery operation. And now they are using the Fourier 80 inflow to measure those products and optimize their battery parameters. They additionally measure simultaneously with EPR to detect the radical formulation and gain insights into the reaction mechanisms. So I think that is a great example of how all the pieces can come together to advance the field of science. And with that comment, I would hand it over to Alec.
So in this part, I'll be talking about applications of how we can use the Fourier 80 in the lab. We'll begin with how to kind of manage expectations, kind of aimed toward people using high field spectrometers, managing expectations as you move to the benchtop system at 80 megahertz. And then we'll take a look at two case studies, the structural analysis of brucine and poloxamers. So first up, for those of us familiar with using superconducting magnets, here we have a 400 megahertz spectrometer, and this is a sample of brucine. It's got all of the features that we're used to seeing in NMR, nice multiplets and well-resolved peaks. When we take that same exact sample and put it on an 80 megahertz spectrometer or benchtop system, we get this resulting spectrum. So it does look quite different, and it can be pretty off-putting to begin with. So we'll go over some of what makes that spectrum look so different, some of the main features. So first up is the topic of resolution. So this is referring to the line width of the peak. And so here we're looking at TMS at 400 megahertz TMS peak. So it's good in both cases, just generally speaking. On the benchtop spectrometer, you will have broader lines. A major component to the change in what you see is this change in the spectral dispersion. So we see at 400 megahertz, our peaks have quite a bit of space between them. When we take that to the benchtop, everyone's much closer together. So they're really close neighbors to each other with very little space in between. And so that is the reduction in spectral dispersion that we see on a benchtop. This major impact on how coupling looks in the resulting spectrum. So again, 400 megahertz, we're looking at pomoic acid here, and we see multiplet structures that we know how to analyze and interpret. But that same exact region on the benchtop system looks quite a bit different. That's because the coupling is no longer first order. So it becomes stronger coupling, and it just makes the spectrum look different. And so these are some of the main changes that we see moving from high field to the benchtop, but it can still be quite useful, as we've seen, plenty of examples of today. So this leads me to this case study, the structural analysis of brucine. And so this is a 1D proton spectrum we get with one scan at 100 millimolar concentration. In our aromatic region, we do have some nicely resolved peaks with nice separation. Of course, they're singlets for the most part, so that looks fine. But in that aliphatic region, there's quite a bit of overlap. And so how we can still make use of this is turning to 2D selective, 2D experiments and 1D selective experiments. So first up, I just show a cozy to show you that you can get some more information from this just by moving to a second dimension. And I'm going to highlight really some correlations we can see quite easily. So those protons on carbons 19 and 10 give us a nice to interpret correlation in pink. We see those aromatic peaks giving us a nice cross peak, as well as the vinyl proton on carbon 6 and the protons on 11 give us a nice cross peak. But we can see that that vinyl proton has some additional coupling partners that's a bit hard to see because of all of the overlap we have in the aliphatic region. So this is where turning to those selective 1D experiments is really quite useful. So the idea here is we're going to selectively irradiate that vinyl proton on carbon 6. We run a 1D selective cozy here. This we can do in 2.5 minutes. We're targeting kind of our stronger coupling, so we're selecting for a J of about 11 hertz coupling, and we see a pretty strong response for that proton on carbon 11, the protons on carbon 11. You can run the same exact 1D selective cozy, but selecting for that longer range correlation. And so again, in 2.5 minutes, a J coupling of 3.5 hertz, we see those longer, further away coupling partners. Protons 16 and 22 are coming through. And lastly, we can go all the way to a 1D selective toxy. So with a 120 millisecond mixing time, we can get a much better idea of the entire coupling network here for this proton, and the added benefit of the correlations being in phase rather than anti-phase. All put together gives you a very nice picture of your system and how to kind of take your 2D cozy and then really get into the details on a benchtop system. So we can also run ROSI and get that type of through space information to get an idea of the structure of our molecule. And so here we have a ROSI spectrum we take in 1 hour. You can see nice correlations there. We can in fact use 1D selective cozies on those aromatic protons to individually detect the methoxy groups nearby. So we'll see an example. First up, we selectively excite the aromatic proton on carbon 9. That gives us that methoxy group for carbon 14. And then we can also selectively excite the aromatic proton on carbon 8. We see the other methoxy group at 15. So now we can actually see those two methoxy groups in separate spectra, as well as pick up a little bit on those protons at carbon 21. So this can help as an example of trying to assign this structure if we were doing that. And last but not least, the workhorse experiment for structure elucidation on high field systems doesn't let us down on the benchtop. So this is multiplicity edited HSQC. We get this nice information. I will just say the F1 projection here is from a proton decoupled carbon spectrum here. So this was acquired in 13 minutes on a 1 molar sample. And we do see again in that aromatic region those well-defined contours, and going to that carbon dimension really gives us a lot of additional information, very helpful. But going back to those methoxy groups, we should see 2 separate contours for them. Right now we only see 1. So we'll talk about how we can potentially get that additional information. So that HSQC was run with 128 T1 increments at 11 minutes. We can use non-uniform sampling readily available on the Fourier 80 to bump that up to 512 T1 increments in the same time span. We see a better resolution in our F1, but those methoxy groups still are not quite separated. What we can then do is a band selective HSQC, selecting this yellow region of the carbon spectrum. This then allows those methoxy contours to come through essentially separately. So that's kind of the different kind of tricks you can play using selective experiments to get that additional information on a benchtop system. Next, I will talk about poloxamer analysis. So this is pluronic F108. It is a polyethylene glycol, polypropylene glycol block copolymer shown here. The 1D spectrum is quite simple, so just 2 peaks. If we take a look at the multiplicity edited HSQC, it gives us a bit more information here. So we can see that methyl group in the polypropyl region gives rise to essentially that signal at 1, and then all of the rest of the protons in the molecule come together to that composite peak at 3.5. But that is in fact all you need to be quantitative here, at least to get the percent ethylene oxide concentration. You just take those integrations from the 1D spectra, and we can determine an ethylene oxide concentration of 82.2%, which agrees quite well to the certificate of analysis, which says 82.5. So as we saw earlier today as well, you can indeed be quantitative with the benchtop. And lastly, with the adjustable temperature feature of the Fourier 80, you can actually monitor phase transitions. So here, this is again pluronic F108, this time 17 weight percent in D2O. And so we can see from this diagram here, at that concentration and at room temperature, we exist in a liquid phase. As you elevate that temperature, you enter this hard gel phase, so it becomes more of a solid. And so on the Fourier 80, we start at 25 degrees and we ramp up to 55 and 10 degree intervals. And we can see that broadening of the peak, telling us we're getting more of this solid phase. So you can use that adjustable temperature feature to your advantage for these types of applications. All right. With that, I'd like to give a big thank you to Ivan for organizing and inviting us to this event. A special thanks to Clemens Anklin and Amy Freund, as well as everyone here in person and remote. Thanks.
So questions?
What's the temperature range?
25 to 60 degrees Celsius.
Thank you.
You showed a line shape, high resolution versus benchtop.
Yes.
Can you give me some numbers
For the
for the line shape?
I don't have a number off the top of my head, but the brucine, like this,
No, I'm talking about, the next one, yeah.
this one.
Yeah.
Oh, so this actually, so this is the TMS peak. So I don't have
I understand. What are the numbers there? Do you know?
No, I don't for the
The
TMS, I don't.
50%, 0.55, 0.11.
Yeah. Okay.
0.11 is 50. What about point or 50%? LWHH,
0.4, I believe.
0.4. 0.4 over 15 is, okay.
Okay, well, thank you. Very interesting.